All right, everybody, this is section 9.7, Taylor's polynomials. And there's also Maclarin polynomial, and it's the same thing as a Taylor's except C equals 1. And this slide says and approximations, but we are not doing approximations. So what we're looking at here, hang on, let me move this. What we're looking at here is we want to create a polynomial that kind of matches, is an approximation of a function that we're dealing with. If you look here, here's a curve. And then this is a line. And what we want to do is we want to find the slope at a particular point. So we could, if this slope matches this slope at a particular point, we want to try to get the polynomial to match up the other graph. We'll have two graphs, and we want them to match up the other graph as closely as possible. Just to try to do an approximation for like the natural log. If we have the natural log function, we want to create a polynomial to mimic that natural log during a short span. And if you look at, and if we just look at this short span here, right here, this short span, these two graphs are very similar in that short span. And that's what the polynomials that we're going to do today do. They mimic the functions that we're dealing with as close as possible during a span of it. All right. And once again, this is just a equation for a line, y equals mx plus b, and this is the slope. A1 is the slope, and first degree polynomial. So I just wanted to show you this is a polynomial, y equals mx plus b. And the slope is the A1, the y-intercept is the A0. And that's what we want to do. We want to create a polynomial. Polynomial is x to a power, right? I mean, this is a polynomial. And we want to mimic this. So that's what we want to try to do. We want to create a polynomial to actually mimic the other thing we're dealing with. And they're just showing you a little bit here. If you have e to the x and you put a 0 in there, you get 1. If you take the derivative of this e to the x, you still get e to the x. You put a 0 in there, you get 1. The derivative is the slope. So we can get if we have a slope on our original problem, we can find the slope at a given spot on that graph. I know I'm rambling on, but we'll get to where we're trying to get to. Let's see. Once again, we're trying to mimic, we're trying to get as close to this graph as we can right here. And if you notice, these two graphs kind of match up as close as we can. This is the e to the x graph, and this is the polynomial. And if we want to try to match this, this is what we're creating. We're creating a polynomial using the method that we're going to be learning right now. And it's just a quick little formula. So Taylor series, this is the formula we want to write down. So if f has a n derivative, has n derivatives at c, then the polynomial fc, the derivative, here's the derivative with plugging c in, x minus c. The second derivative with 2 factorial with a power of 2 and so on. Then the next term would be the third derivative with c over 3 factorial, x minus c to the third power. And there's what we got. If we put, once again, if we put a 1 in here, we can put a 2 in here, we can put a 3 in here, and so on and so on. Here we're putting a 0 in here, or depending on what they tell us C is. I mean, normally they tell us what C is. So this is the formula we are going to be using. So you should have that written down. Oh yeah. And if it, I mean, this is called, once again, a Taylor polynomial. And 9.10 is where we do a Taylor series, but this is the Taylor polynomial. Now, if we want to call it a Maclaurin polynomial, then we have to, right here, we have to use C equals 0. But if we're not using C equals 0, if we're using C anything else, it's a Taylor. But Maclaurin is when C equals 0. All the C's will equal 0. So that, I mean, it's the same thing as a Taylor, except C equals 0. So we're going to do it for this problem right here. Find the nth Maclaurin polynomial. And so the first thing, I guess that was it. Let's take a look at this. So once again, Maclaurin, if we say Maclaurin, then C equals 0. So I'm going to write down the formula again right here. And f of x equals f of c plus the first derivative of c, x minus c, plus the second derivative of c, x minus c. On the homework or on the test, I would tell you to like do 3 of these or something, take it out to, well, n is 3 or something. Since it's the second derivative, we do 2 factorial. And then the next one would be 3cx minus c over 3 factorial. Third derivative, we use 3 factorial, and so on and so on. So Maclaurin c equals 0. Here's our function. And so I'm just going to put the functions down here. If I ask for the first derivative of e to the x, I mean, this is a really easy one. If I ask for the second derivative of e to the x, it's still e to the x. If I ask for the third derivative of e to the x, I still get e to the x. So, I mean, the derivatives, I mean, the hardest part is taking the derivative 2 or 3 times. And this is a really easy problem in the PowerPoint they gave me. When we get to the homework, I think we still have some easier ones there. There's a couple that's challenging. So first, f of c, we're putting e, and c is 0, e to the 0. E to the 0 is 1. First derivative, plug 0 in there, I get 1. And then I get x minus 1. C is 1. Or wait, C is 0. X minus 0. Maclaurin C is always 0. Then the second derivative is right here. Plug a 0 into it. E to the 0 power is 1. x minus c is 0, and then 2 factorial. 2 factorial is 2. Same thing here. The third derivative is e to the x plug 0 in there. You get 1 x minus 0. 3 factorial is 6, and so on and so on. So if we then look at this, this becomes 1 plus 1 times x is x. 1 times x is x over 2. And then this becomes x over 6. And so on and so on. So this is the Maclaren polynomial we've created here. Wait, I'm missing something. I am missing something. There is a square here and a third here. So this, I mean, the formula has an n. So if the formula has an n, so if n is 1, there's a 1 here. N in this case is the same thing as the derivative or the factorial. So there's a 2 here. And then there's a 3 here. So this is, because this is a polynomial, we have to have powers. And then 3. All right. So this becomes, oh, hang on. What happened? I'm going to erase everything I did. This is what it becomes, pretty much the same thing. I wrote down the 1, the x, 2 factorial. I mean, you could write it like this, or you could say 2 factorial is 2, or 3 factorial is 6. But then the nth term, if you look at it, if this is n0, n1, n2, n3, you see, so these are the n's. So this is going to be so to do the nth term, the only thing that deals with the n is whatever the nth term is here. We have an n here and an n here. So if we wanted to do the 6th term, we would do 6 factorial and then x to the 6th power. So this is the Maclaren polynomial. Now, if I use the same, I don't have the Taylor one example, but let me do that and just say, and this is what would happen for a Taylor. They would tell us what C equals. C equals 1 in this case. So if this Taylor, let's say C is 1, and we would go through the same process. I'm going to write down the formula again. F of C plus the first derivative with C in it, x minus C, plus the second derivative with C in it, x minus C squared. Since we're doing second derivative, we got to do squared over n factorial. And then we're going to do the next one. X minus C to the third over, oh wait, we said 2. This is 2 factorial, and then this would be 3 factorial. And there's the, oh, I was writing the formula down, sorry. N factorial, n factorial. So when we do this, it's still, the function is still e to the x. I'm not changing anything. So the derivative is e to the x. The second derivative is e to the x. And the third derivative is e to the x. So except now we're plugging 1 into the c. So if we just have the function, this is our function, and we plug 1 into it, we just get e to the 1 power. The first derivative, you plug 1 into it, you still get e to the 1 power, which is e, and then x minus c is 1 in this case, so we put a 1 here. Second derivative is the same thing, plug 1 in there, you get e, x minus 1, c is 1, squared over 2 factorial. That should be a plus. And then finally, this is e x minus c to the third power over 3 factorial, which is 6. So these are the first 4 terms of the polynomial. If they ask you, write out 4 terms of the polynomial. And that's kind of what they'll do on the test or the homework. All right, so let's go to the homework. I mean, a lot of times these PowerPoints don't make sense unless we actually look at some examples in the homework. I mean, you just use that formula. It's pretty simple. The hardest part is if you're having problems with some of the derivatives. All right, let's see. Let's get to that homework. If it lets me, it's not letting me click on anything. And we're on 9.7. I saw like half the class hasn't even got through 9.2 yet, so I'm worried. All right, here's 9.7. Okay, so the first 2 questions, they look hard, but it's a lot easier than you'd think. It says, match the Taylor polynomial approximation to its function. So if we look at this, this is the function. Right here. And this is the Taylor polynomial. I mean, this is what we could create if we wanted to, what they're going to ask us after question 2. And they want to know which one is it. Are these even labeled A, B, C, D? I don't think so. A, B, C, and D. Just by looking at these, you should be able to tell me which ones are A, which is the correct answer. And I'm going to show you, this is the e to the negative x squared over 2. This is the, if you look at that, that's the same, that's the function that we're looking at, e to the negative x squared over 2. But the question is, which one of these lighter ones, if you can see the light ones on your screen, these are the light ones here. Which one of these light ones does this function match up? Can anybody tell me A, B, or C?
It's probably going to be B, since if you look at the x to the 4th, the highest power is even. So we know that there's going to be 3 turns in the graph.
Well, I'm not even looking at the terms, but you're right about the x to the 4th. X to the 4th is a polynomial where both endpoints are going up. And this is B is the only one where both polynomials going up. And you're right, there'd be 3 turns, 1, 2, 3. It looks like a W. And I mean, this one here turns and turns and it goes back up. And this, I think, is just a straight line. And this is a polynomial, but with a negative, probably a negative x squared. So yes, the answer is B. So I mean, you just have to look at the function and seeing which one matches up. I mean, this is just from algebra. So if we go to number 2, I mean, that's all you had to do is pick the correct one. If we go to number 2, this is the polynomial is an x to the 3rd. And if we look at x to the 3rd, this, if you remember x to the 3rd graphs, they look like this. The right side is up, x to the 3rd. the right side is up, the left side is down, and that's what this one is doing. It's kind of hard to see. It's really light. That's what it looks like there. So those should be easy to spot if you just remember the way you're going to be graphing it from algebra. Okay, so now we're going to do, I'm not going to do number, well, I guess I could do number 3. Well, we'll just talk about these. So now it says find the nth Maclaurin polynomial for the function. So once again, as soon as we say Maclaurin and not Taylor, as soon as we say Maclaurin, you need to write down C equals 0. As soon as you say Maclaurin, C equals 0. That was in the theorem there. Our function is secant x, and then we start taking derivatives. If you take the derivative of secant x, you get secant x, tangent x. You can look that derivative up. Then it gets a little crazier. Taking the derivative of this, you might have to use the product rule. And I think you're going to have to use the product rule. See, sometimes the derivatives get a little harder. So I use the product rule. I'm not going to go through that right now. But I mean, they show you that what the answer is for the second derivative. But try using the product rule and you should get this secant to the third plus secant x tangent x. Sorry, I'm running out of room. And the whole the tangent x is squared, not the secant third. The tangent x is squared. And so when you plug 0, when c equals 0 in this case, well, let's write the formula down again. I mean, I like to have that formula right in front of me. F of c plus derivative of c, x minus c, plus the second derivative, plugging c in there, x minus c squared, all over, this one is 2 factorial. And I think that's all we're going to do the second. Yeah, that's all they wanted us to do here. So if you look at secant squared or secant and you plug 0 into it, that equals 1. I'm going to try that on your calculator. Then if you take the first derivative, secant x tangent x, and plug 0 into that, secant 0, tangent 0. If you notice, one of these two, you're going to get 0. So the whole thing is 0, plus, by the way, x minus 0. But one of these is 0, so the whole thing becomes 0. And then finally, when we do the last one, it looks like you get 1/2. The last one, when you plug that in, looks like you get, oh, it looks like you get 1. When you plug 0 into here, looks like you get 1, but you have a 2 factorial on the bottom of 2, so you get 1/2 with the x square. And there's our Maclaurin polynomial. Well, this is our Maclaurin polynomial. And so that just turns to 0. So it's 1 plus 1 over 2 x squared. So that one, I'm going to say that's a tough one because of the, you have to do a little work to find that second derivative. You have to definitely, I mean, the product rule is no big deal, but it's still a little time consuming. And on the test, you'll have something easier to take the derivative, maybe like question 4, something a little easier. This is the Maclaurin also, so I can't stress this enough. As soon as you see Maclaurin, you're going to say C equals 0. And we're dealing with the function sine x. Take the derivative. And here it says, find the nth Maclaurin once again. Derivative of sine x is cosine x. Then the derivative of cosine x is a negative sine x. Then I guess they're doing they're doing 6 of them. You don't really need to do 6. I think you can figure it out once you do 3, maybe 4. Yeah, I would say once you do 5, you see the pattern there. You try to do it till you see the pattern. The derivative of negative sine x is negative cosine x. And then instead of tick marks, we start going to the 4th derivative. We're going back to sine, so we have to change this, the sign of it again. So we get sine x. And then f of 5, derivative of sine x is cosine x. And so once we plug this in, the formula says f of c. So we're going to plug 0 into sine x, and we get 0. I mean, look at your unit circle. I should have the unit circle in front of me. Class. It's on the floor over here. Once again, the sign of 0 is 0. So we get a 0 for this first term. Then the second term is this, the second derivative. We're going to do the second derivative, x minus c. C is 0 in this case. And the second derivative is the cosine of 0. Cosine of 0 is 1 times x minus 0 is x. So we get 1x. The third term is a negative. I'm going to just put a negative next to it. If you put a 0 in, once again, if you put a 0 in the sign, I should write it down. I want to write down the formula first. X minus, in our case, 0, because c is 0 squared over factorial, which is 2 factorial. So the next one, this second derivative is 0. You put 0 into sine, negative sine x, you still get 0. So this whole thing is going to become 0. This is right here. You plug 0 into sine x. If it's negative or positive, you're still going to get 0. And then I'm going to do one more. The third derivative, x minus 0 to the third over 3 factorial. So here's the third derivative. You put 0 in there. Cosine of 0 is 1, so we get a negative 1. So this becomes a minus 1. X to the third. 3 factorial is 6. So I end up with 1x minus 1/6 x to the third. If you look, there's 1x minus 1/6 x to the third. And then if you do 4, you see 4, it would be 0, and then 5 would be the next one. And they're showing 5 factorial. 5 yeah. 5 factorial is 120. 5 times 4 times 3 times 2 times 1. So this is the series. Oh, I was going to say, how did they know where to stop? But they said they wanted you to do 6 of them. So that's why they took 6 derivatives. I didn't even see that at first. There, they wanted you to do 6 of them. So they wanted to take it all the way to 6. And this is what they got. So that, I mean, all the hardest part is taking, once again, like in question 3 up above, is taking the derivative. Here, this was a pretty easy derivative, just as long as you understand the derivatives with signs, the sign and its derivative and all that. Let's take a look at this one really quick. Here, they're going to do 4. And this is a Taylor. So finally, we got a Taylor. Don't forget, Maclarin is when C equals 0. This time it's Taylor, and they tell us C equals 6. So first we have our function. Maybe I should have this over to the side a little bit more. Natural log of x. The derivative of the natural log of x is 1 over x. Another way of writing it, and this is the way I recommend it for this problem, is x to the negative 1, because it's easier to take the second derivative than you bring the negative over and then subtract 1. And so you get x to the negative 2. So for the third one, you bring the negative over, it turns to positive, and you subtract 1, you get x to the negative. Oh, you don't just bring the negative, you bring the whole negative 2 over, sorry. So there's a negative there already, you bring a negative 2 over, and then you subtract 1, you get negative 3. Negative, negative in front of it becomes a positive. And then finally, they want us to do 4. Bring the negative 3 over. Negative 3 times 2 is a negative 6. And then subtract 1, you get negative 4. Okay, so here's our derivatives that we took. And now we're just going to plug them into the formula. Start off with f of c. Plugging 6 into there, and we get the natural log of 6. Next, the once again, the formula is first derivative, plugging c in there, then we get x minus c. So here's the first derivative. You plug, or here, you plug 6 in there, you get 1/6. X minus 6. C is 6. So that's what, why do I have this extra X here? I don't think, I put the X, the X's goes inside the parentheses. There we go. Okay, and then the second derivative, plugging c into it with the x minus 6, c. So here's the second derivative, and you plug 6 into it. It's the same thing as writing this 1 over x squared. You plug 6 into there, you get negative 1 over 36. Negative 1 over 36 x minus C is 6. And if you look, I mean, here's our series. This natural log is our first one, 1/6x. Oh, I forgot, by the way, don't forget, I forgot, we did here, it was 1 factorial, but here there's a 2 factorial on bottom. So 2 factorial is 2. And so when you do 2 factorial, 136 divided by 2 is the same thing as 136 times 1/2. This becomes 1 over 72, x minus 6. And don't forget, since it's square, we have to put a square there. I have the formula right in front of me, and I forget that so often, but you don't forget that. If you look, there's our first term. Here's our first term, our second term, our third term, and so on and so on. So you'll keep on going. You're going to do it 2 until we have a power of 4. All right. And I think that's all I wanted to show you. If you look there, I mean, it's really simple assignment. The hardest part is taking the derivative and having the formula right in front of you and making sure. I recommend, see, I was skipping like little steps. Have the formula written out all the way in front of you. And then below that, plug everything into it. Get rid of all the zeros. If there's a term that's 0, they're going to get rid of it. And then just like here, up here, if you look, we don't need this anymore. So our answer is 1 plus this. And you do have to, don't put factorial in your answer. You do have to take the factorial. 2 factorial is 2. So you, in your final answer, don't put factorial, actually multiply the factorial out. All right, and that was quick. That was 45 minutes. Hang on. Any questions over